aging effect on APCVD-Grown 2D MoS2 Monolayer in NO2 gas sensing. And the presenter is the Chandrabhan Patel from the Indian Institute of Technology. Please welcome our presenter.
So, very good evening to all of you. So, as I'm going to talk about aging effect on the APCVD-Grown 2D MoS2 in different environments and its application for NO2 gas sensing. So, so this is a presentation outline. I'll talk about the specifically introduction, methodology, followed by the result and discussion, conclusion and future work, references. So as we know, a gas sensor, as in a human being, we have 5 senses to generally sense the environment in our taste or color or different touch sensors. So these are the basic sensing mechanism actually in the human body. So that's why here we are actually trying to explore the NO2 sensor, which causes various disease, and it also causes the every year approximately 7 million people have lost their life due to the air pollution. So that's why we are going to interested to detect the NO2 at a lower ppm. But currently our traditional gas sensor technology is a metal oxide based sensors, and major limitation with the traditional gas sensing technology is poor selectivity. It has a poor selectivity compared to the target gas, or we can say the higher interference with other gases. Poor sensitivity, it cannot detect up to the ppb level for the target gas, and high operating temperature. It always requires certain temperature more than 200 degrees centigrade for the gas sensing application. And another major limitation associated with the metal oxide based sensor is unavailability of real-time interfacing. So here I have tried to actually develop a sensor using a 2D MoS2, which actually cover the ppb level sensitivity, and it shows the ultra selectivity towards the NO2, and integrated integrated with the IoT circuit for real-time operation, which actually provide the also alert facility. If the NO2 concentration exceed in the hazardous range, it also provide the daily and weekly or monthly exposure history of the NO2. So this is actually a synthesis process for the monolayer MoS2. So here I have used the solution assisted process monolayer growth for the MoS2. So MO3 powder dissolved in ammonium hydroxide solution, and this ammonium hydroxide solution is further spin coated on SiO2 Si substrate. This MO3 coated substrate is kept on the bottom of the alumina board, in another SiO2 Si substrate kept on top of it to actually trap the sulfur flux between these two substrates. In another alumina board, we take the sulfur powder. So this is actually camera image, how we kept the samples and the sulfur powder. And these two alumina boards loaded in the respective heating zone inside the quartz tube. So here sulfur is loaded at 180 degrees centigrade, while MO3 or substrate loaded board kept at 800 degrees centigrade. Distance between these two alumina boards it is optimized, and which is 31 centimeter. And argon and oxygen is used as a carrier and assist gas respectively. This is a temperature profile, carrier gas flow rate profile, and assist gas flow rate profile during the growth of monolayer MoS2. So this is the optical image, single crystal MoS2, which actually grown by this APCVD system, and its further characterization to investigate its topology or thickness. So which shows 0.71 nanometer thick, which actually highlighted that it is a monolayer MoS2. For further validation, done the Raman spectra, which shows the in-plane and out-of-plane peak difference between the two peaks, which further confirms that deposited triangle is monolayer MoS2. For elemental validation, done the XPS analysis, and for this actually Hardaf analysis done actually to its morphology, and this is actually STEM analysis for the elemental distribution of MO and sulfur. So after characterizing and successfully depositing the MoS2 monolayer, done the transfer process via surface energy assisted transfer process. So polystyrene is used as a carrier polymer to lift off the MoS2 from the deposited SiO2 Si substrate. So with the help of polystyrene, we can lift off this MoS2 monolayer. We spin coat the polystyrene and we immerse this substrate into the DI water. So water will be penetrate between the MoS2 layer and SiO2 Si substrate. Due to its opposite nature, hydrophobic and hydrophilic nature, water will be penetrate, and we can easily lift off with the help of polystyrene. Further, polystyrene is dissolved in toluene solution by repetitive immersing in the toluene solution, and only we got the MoS2 on this interdigitated electrode structure already grown on the sapphire substrate. So here this is on glass substrate. We have a interdigitated electrode structure. Here I have shown the optical image of the transferred MoS2 crystals on this interdigitated electrode structure. So this is the optical image of it. For after that, done the manual wire bonding process for this interdigitated electrode structure on this particular PCB into the circular form, and done the packaging and packaging of this structure to prevent from the dust particle, and on the top of it for the exposing area use the fine mesh to actually expose the gas sensing gas from on the top of it. So this is the, we can say this is a gas sensing module. We have now actually packaged it. After doing this wire bonding process, develop the resistance readout circuit for measuring the change in resistance in the real time. So this is the first Proteus-based simulation tool we have used for the resistance readout circuit, which can measure the change in resistance, and also tested this resistance readout circuit on the breadboard. In the next stage, we have developed the layout, and finally it is tested on the PCB platform. So this is a microcontroller based resistance readout circuit, which actually can measure the resistance range from kilo ohm to the mega ohm range, which is sufficient enough for the measuring the change in response of the MoS2. So here I have shown the each steps. First, PCB fabrication or layout designing. After that, integrated other components, LCD, buzzer, and other components keypad here for real-time development. In the simultaneously, we have also developed an Android application which shows the actually NO2 exposure on daily, weekly, and monthly basis, as well as alert facility if the gas concentration or NO2 concentration comes into the hazardous category on the registered user mobile number. So we have also integrated here GSM module. And in the GSM module, we will fix the same SIM and SIM card, and we actually included some few numbers which actually user going to use this product. So if the gas concentration exceeded near about this product, so it will directly initiate a first message on the registered user number. If register is not sending in a reply yes or no, then it will initiate a call, automatic call on the registered user number, and it will be continue will be in a loop till now user didn't respond to this particular sensor. So here are the developed products for the NO2 gas sensors by using this MoS2 2D TMD material grown by CVD system. So these are the three lab packaged gas sensor product. You can see these modules or packaging we have actually done via 3D printers. So here you can see. Now I'll come to the final point. After developing this particular product, I feel certain difficulties. What was the difficulty? Major limitation I have found this product. After certain times, this product is response of this product is going to down. So that was my actually intuition, how actually this response is not constant, why it is going to down. So I was curious and I have tried to investigate the material side first. So in the material side, I have deposited the same MoS2 crystals using the same method and kept in different environment. First, grown CBD, APCVD-Grown MoS2 material kept in glove box in the inert atmosphere. Another MoS2 samples kept in the desiccator vacuum environment. In another MoS2 samples kept in the air environment. And done the environmental study with the time, prolonged time. So here for after 4 months, here I have shown the result only for after each 4 months. But this study I have done for each month. After at the end of each month, I have taken the optical images and tried to find some defects or some in the optical images first. So as you can see, the samples kept in the glove box and desiccator, we found that nothing actually, we didn't found any defects or any actually degradation on the MoS2 surface. But the samples kept in the air environment, which is in the lab environment at normal humidity condition, these samples we have found that after actually more than 8 months, we have found a lot of cracks on the surface, and it started from the nucleus side or at the center of the triangle. So we have found that lot of cracks were there on each triangle. So this study we have done. And so these are the sensing results. I have also, after that, I have used the same transfer process for each 3 samples which samples kept in glove box, desiccator, air environment, and measured the gas sensing response. So significantly, I found that the sensing response is going to decrease for the samples kept in the lab environment or in open air environment. This is the actually I have also compared our sensor with the renowned sensors which are already available in the market. So here I have shown few actually. These are the technical term detection range or limit of detections, operating humidity and cost near about. So this is the approximated cost, because this is till now no actually we are not producing on large scale. This is only a lab scale cost we have produced at the lab scale. And this is a calibration certificate we have achieved for our sensor with the certified company. So here, this was the result. But here I want to add one few point. In this work, I have actually highlighted the result only for these three environment. Now I have also studied few result, and because that study is continuously going on, and different humid conditions. Let's suppose 47% relative humidity, 75, 87%. And in UV exposure. So these samples I have kept in, and I'm continuously observing these samples as well, how the degradation rate is going to faster in different environment. So that study is not continuously concluded. So that's why I didn't shown here. So this is the conclusion for this presentation. So I have grown the APCVD-Grown monolayer MoS2 kept in different environment, in glove box, desiccator, and lab environment. And we have found that the samples kept in the open environment, it has a large degradation as compared to the samples kept in the desiccator and glove box. And in the future work, I am trying to explore the aging effect on the number of layer of MoS2. Is there any effect if we are growing bilayer, tri-layer, which are more stable compared to the maybe monolayer? So that's why I'm trying to also explore this particular and a correlation between the how I can improve the stability of the CVD-Grown monolayer by controlling the growth parameter. So this is also I'm looking for it. This is all about the publication recognition references. Thank you very much.
Okay, thanks for the nice presentation. Now paper is open for question or comment. Is there any question?